Good morning, ladies and gentlemen. I'm back again. Remember that in the past slides, we concentrated on the cycling of nitrogen in nature. And as part of that cycling of nitrogen in nature, we spent quite a great deal of time on the process of nitrogen fixation. Remember, the process of nitrogen fixation contributes towards the cycling of nitrogen in nature, in the sense that the nitrogen that would have been lost into the atmosphere, mainly through volatilization, but mainly through the denitrification process, can be accessed back and be brought back into the cycle only by those plants that are able to fix the nitrogen gas in the atmosphere, because they make an association with nitrogen fixing bacteria. And these plants are called nitrogen fixers, and they are largely legumes. So when that nitrogen is accessed from the atmosphere, it can be converted into a form that a plant can use. But let's not forget that when this plant dies, when a nitrogen fixing plant dies, because eventually a plant will die at some point, or a leaf from this plant dies, the nitrogen in it will be released back into the soil. So that cycling will keep on happening. So if we assume the nitrogen is in the soil, remember the nitrogen can be in the soil either in the form of ammonium, that is if nitrification does not take place, or in the form of nitrate, that is in a case where ammonium has been converted into nitrate. So you have got two main forms of nitrogen in the soil: nitrate and ammonium. Nitrate being a negatively charged ion, and ammonium being a positively charged ion. Both are two forms of nitrogen, and one can be predominant in a particular soil depending on the soil conditions, and the other can be dominant on another environmental condition depending on conditions prevailing in that environment. So when this nitrogen is available in the soil, our main focus now is how does a living plant make use of it? So our main focus is going to be the absorption of this nitrogen, and from there, the processing of this nitrogen by the plant. Remember, the main reason why a plant absorbs nitrogen from the soil, it's for it to be able to use that nitrogen to make its own amino acid. Also to use that nitrogen as a component of its nucleic acid, and so on and so on. That is the main reason why plants keep on absorbing nitrogen from the soil. Remember, you can go and look at the structure of an amino acid. There is no amino acid that does not contain a nitrogen atom or a nitrogen element. So basically one can say no carbon and no nitrogen, then no amino acid. and no amino acid, no proteins. So you can understand if there were no proteins, that basically means no life. Because all enzymes are proteins. And proteins play a very important role in the life of a living organism. It's one of those organic molecules of life, in addition to carbohydrates and lipids and nucleic acids, which play a very important role in the life of plants. So the focus is the absorption of nitrogen by the plants and what happens after this nitrogen has been absorbed. You can see from this slide that I'm currently focused on. It shows you nitrate and ammonium being absorbed by the root of the plant. It also shows you that ammonium can be found in the root of the plant, and that ammonium can be as a result of the nitrogen that has been fixed by the nodules that are part and parcel of the roots of the plant. So roots can get ammonium from the nodules if the plants are nitrogen fixers, but they equally can also get ammonium by absorbing it from the soil. Plants, however, can only get nitrate by absorbing it from the soil, because the end product of nitrogen fixation is ammonium and not nitrate. So which means nitrogen in the form of nitrate can only be absorbed by the roots of the plants from the soil. So after the absorption of ammonium and the absorption of nitrate, this nitrate and this ammonium can be processed within the roots of the plant, with ammonium largely being processed within the root of the plant. But nitrate can either be processed within the root or it can be transported to the leaf where further processing will take place. So you can find nitrate being processed by the root, and therefore what is going to be transported to the leaf are the end products of the processed nitrate, which is largely amino acids. Ammonium is predominantly processed within the root because it can be toxic if it reaches the leaves of the plant as ammonium. Therefore, it is processed immediately after being absorbed, and the amino acids that are formed after the processing of this ammonium are also delivered to the leaf of the plants via the xylem. So nitrate, part of it can be processed within the root, but part of it can be processed within the leaf. In cases, all of it is processed within the root, and in other instances, all of it is processed within the leaf. This differs from one plant species to the other. Thank you. Hello, I'm back again. Let's continue. What you can see on this slide is nitrate and ammonium adapted plant species. Please go through this slide. Everything is so self-explanatory. All I can tell you is those plants that are adapted to the environment or the soil in which the predominant form of nitrogen is nitrate have been given the term calcicoles, whereas those that are adapted in an environment in which ammonium is the predominant form of nitrogen are given the term calcifuges. So I'm gonna skip this slide now. The next slide deals with the absorption of nitrate. And on this slide, the is what is called nitrate transporters. These are enzymes which plays a role in the movement of nitrate from the soil across the membranes of the root cells into the root. They are called nitrate transporters. And you have got two types: those that operate when there is a high concentration of nitrate in the soil, and those that operate when there's a low concentration of nitrate in the soil. You can go through the slide, and the last part of this slide deals with some of the factors that can influence the absorption of nitrate. Things like the availability of energy-rich compound, things like the temperature of the soil, and lastly the pH. I'm gonna skip this slide. It is just showing you the nitrate transporters, how they operate as SIM ports or uniports, but don't worry much about this slide. I'm skipping it. You can also skip it if you wish to. Now, remember I said nitrate can be absorbed and be processed within the root, but in other instances, it can be transported from the root to the leaves of the plant after being absorbed by the roots of the plant. Now, because nitrate is not toxic to the plants can keep on absorbing nitrate, storing it in their tissues, absorbing, storing for later use. Now, remember, nitrate is a negatively charged ion. So some people once questioned or came up with a question as to, when the plant keeps on absorbing a negatively charged nitrate, doesn't this affect the electroneutrality within the tissues of the plant? Remember, the assumption is in the plant there is an equal number of negatively charged ions and positively charged ions. So they balance each other out, and the ultimate charge of tissues in the plant is neutral, what we call electron neutrality. So the question is, as the plant keeps on absorbing nitrate, which is negatively charged, doesn't this result in a plant having more negatively charged ions in its tissues as compared to positively charged ion? The solution to this kind of a problem has been provided. A possible solution has been provided by some other people who came up with so-called potassium shuttle mechanism. Part of it is explained here, which in a nutshell proposes that nitrate is absorbed into the root of the plant, and upon entering the root of the plant, potassium attaches itself to this nitrate within the root of the plant. Then the potassium nitrate that is formed as a result of potassium attaching itself to nitrate is delivered from the root via the stem to the leaves of the plant. Upon reaching the leaves of the plant, nitrate is dumped within the leaves. Potassium detaches itself from nitrate within the leaves and it becomes free. And within the leaves, there is a negatively charged compound called malate. Potassium attaches itself to this malate within the leaves, and it comes down as potassium malate via the phloem back to the root. Upon reaching the root, potassium detaches itself from malate, and malate is broken down into a bicarbonate and pyruvic acid. The bicarbonate, which is negatively charged, is released into the soil. The potassium is free again, and it attaches itself to another incoming nitrate. So you can see the role of potassium is to transport. It picks up nitrate from the root and it dumps it within the leaves. And within the leaves, it picks up malate and it drops it in the root of the plant. So malate, potassium here, it's considered to be a shuttle. You know what a shuttle does? It picks something from point A, drops it from point B, picks up something from point B, drops it at point A, and it keeps on shuttling between point A and point B. This is what potassium is doing. It picks up nitrate, drops it in the leaf, picks up malate, drops it in the root, picks up nitrate again, drops it in the leaf, picks up malate from the leaf, drops it in the root again. Like that, it keeps on shuttling between the leaf and the root of the plant, making it to be a shuttle. So it is something that accompanies the nitrate, and it also accompanies the malate. How does this help? When nitrate that has been absorbed by the root, it's dropped in the leaf of a plant. That nitrate which is negatively charged, there is an exchange. As nitrate is getting into the leaf, malate which is negatively charged is leaving the leaf. So you can't have more negatively charged ions within the leaf, because as nitrate is entering the leaf, malate is leaving the leaf. Within the root, the same thing happens. As nitrate is entering the leaf, bicarbonate is leaving the root. I meant to say, as nitrate is entering the root, bicarbonate, which by the way is coming from the broken down malate, it's leaving the root of the plant. And in that way, the plant maintains its electroneutrality. And lastly, the absorption of ammonium is not different from the absorption of nitrate, only to say that just as much as there are nitrate transporters, also in the case of ammonium, there are ammonium transporters. Go through this slide and also look at these other factors that affect the absorption of ammonium: carbohydrates, salt temperature, and pH. Goodbye.